Okay, strap yourselves in, listeners. Today we're diving headfirst into the cosmic enigmas that are black holes. And their even stranger counterparts, white holes.
And you've come to the right place for a journey like this. We're going beyond the usual black hole basics.
I thought I had a handle on black holes, but looking at your notes, I realized there's a whole lot more weirdness than I ever imagined.
It's true. Black holes really push the limits of what we know about the universe. Think about it. They emerge from the death of stars, warp the fabric of space and time itself, and might even hold clues to a deeper understanding of, well, everything.
See, that's what always blows my mind, the sheer scale, the power. It's almost too much to grasp. So maybe we should start with some basics, just to ground ourselves. What exactly happens for a black hole to even form?
All right, picture this. A massive star, way bigger than our sun, reaching the end of its life. It's like a cosmic balancing act playing out.
Oh, I like where this is going.
Right. You've got gravity, this relentless force trying to crush the star inwards. But at the same time, you have nuclear fusion happening at its core, pushing outward.
Okay, so it's a cosmic tug of war. Got it.
Exactly. For most of a star's life, those forces are balanced. But when the star runs out of fuel, the outward pressure from fusion, it stops. And gravity wins.
Yeah.
The core collapses in on itself.
It's like turning off the engines mid-flight. Gravity just takes over. So what happens when everything collapses?
That's where things get really wild. The core of this massive star, it shrinks down to an incredibly small point, smaller than an atom. We call this point a singularity. And here's the kicker. All of the star's mass gets concentrated into this tiny, infinitesimal point.
Hold on, all that mass squeezed into something infinitely small. I think I need a moment to process this.
It's mind-bending, isn't it? And surrounding this singularity is where we find the event horizon. You can think of it as a point of no return.
Because once you cross that boundary, there's no escaping the gravity.
You got it. Not even light, the fastest thing in the universe, can outrun the pull of a black hole once it crosses that event horizon. Imagine a cosmic trapdoor. Once you fall in, there's no coming back.
So we've got collapsing stars, singularities, these event horizons. It's a lot to wrap your head around. But, and maybe this is a bit of a leap, don't we have a supermassive black hole right in our own galactic backyard?
We do. Lurking at the very heart of our Milky Way galaxy, we have Sagittarius A. And get this, we actually have an image of it captured by the Event Horizon Telescope.
Wait, there's an actual picture of a black hole?
There is. Of course, you can't directly see the black hole itself. It's black. After all, no light escapes. But the image shows us its shadow, this dark silhouette against a backdrop of glowing gas and dust swirling around it.
That's incredible. But it does make you wonder, if we can't directly see them, how do we even know these black holes are out there? It's not like they send us postcards.
It takes some cosmic detective work. We detect their presence by observing how they affect the stuff around them. Take Cygnus X1, for example. It was one of the first black holes ever discovered.
Oh yeah, I've heard of that one. It's a binary system, right?
Exactly. Cygnus X1 is a black hole locked in a gravitational dance with a companion star. As the black hole pulls in material from its stellar partner, that material spirals inward, kind of like water going down a drain. And that's where things get really interesting and bright.
So we've got this black hole pulling in material, creating this swirling disk of superheated matter around it. It's like a cosmic whirlpool. And this is where things get really bright, right?
Exactly. All that matter swirling around in the accretion disk. It heats up to millions of degrees, partly from friction, partly from the intense gravity of the black hole itself.
Wow, millions of degrees. That's gotta be giving off some serious energy.
It does. And that energy is what tips us off to the black hole's presence. See, all that superheated matter in the accretion disk, it emits X-rays. And we can detect those X-rays here on Earth.
So it's like a cosmic spotlight, but instead of visible light, it's X-rays revealing the black hole's location.
You could say that. It's like trying to understand a hidden object by the way it affects its surroundings. We can't see the black hole directly, but we can see its influence on the material around it.
That's a really cool way to think about it. So it's not just that black holes are these isolated things out there in space. They're actually interacting with their surroundings in these really dramatic, energetic ways.
Absolutely. And those interactions, they can get really interesting. Sometimes they even challenge what we thought we knew about black holes. For example, did you know that black holes, well, they aren't entirely black?
Wait, hold on. I thought nothing, not even light, could escape a black hole. Isn't that kind of their whole deal?
That was the prevailing thought for a long time. Then along came Stephen Hawking and kind of turned our understanding on its head.
Oh, this is going to be good. I can tell.
Right. So Hawking, he proposed that black holes actually emit a type of radiation. It's faint, but it's there. We call it Hawking radiation.
Okay, now my mind is blown. How can anything escape from a place where gravity is supposed to be inescapable?
It all comes down to the weird world of quantum mechanics. You see, at the event horizon, right at the edge of a black hole, you have these things called virtual particles. They're constantly popping in and out of
Or
existence.
virtual particles? Are we talking about ghost particles now?
Haha, kind of. They're more like fluctuations in quantum fields. Pairs of particles and antiparticles that usually annihilate each other almost immediately.
Okay, so far so good. But how does this lead to anything escaping from a black hole?
All right, picture this. A particle-antiparticle pair pops into existence right at the event horizon. Sometimes one of these particles falls into the black hole while the other escapes off into space.
And because they were born together, right at that critical point, the escaping particle can make a run for it.
Precisely. The escaping particle becomes real, carrying away a tiny bit of the black hole's energy with it. And here's where Einstein comes in. Energy and mass are equivalent, remember, E mc.
Oh, right. Of course.
So when the particle escapes with a bit of energy, the black hole actually loses a tiny, tiny bit of mass.
Whoa. So even though nothing can escape from inside the event horizon, this quantum quirkiness happening at the edge allows them to leak a little bit of energy.
You got it. And over ridiculously long periods of time, way longer than the current age of the universe, this Hawking radiation could actually cause a black hole to completely evaporate.
Black holes aren't eternal. They could just fade away. That's kind of beautiful in a way.
It is, isn't it?
Mm-hmm.
But it also leads to a pretty big puzzle, the information paradox.
Uh-oh. What's that?
Well, if black holes can evaporate, what happens to all the information that fell into them? Everything that gets sucked in, stars, planets, even light, it all carries information, right?
That's a good point. So what happens to it all?
That's the paradox. According to quantum mechanics, information can't be truly destroyed. It might get scrambled up, but it's always conserved in some form. So if a black hole evaporates completely, does that mean all that information is just gone?
That doesn't seem right.
It's one of the biggest mysteries in physics. The information paradox. It highlights a potential conflict between general relativity, which governs black holes, and quantum mechanics, which governs information.
It's like needing a cosmic rulebook to tell us which one wins out in this scenario.
Exactly. There are lots of proposed solutions out there. Some involve the information being encoded in the Hawking radiation itself. Others suggest it might be stored within the black hole in some way we don't yet understand.
So the jury's still out on this one.
It is a head-scratcher. It's a problem that continues to fascinate physicists and frustrate them in equal measure. But hey, maybe you'll be the one to crack the code.
Huh. Don't hold your breath. But speaking of things that might not exist, can we talk about white holes now? We've been dancing around them all episode.
Of course. Buckle up, because if you thought black holes were strange, white holes are about to get even weirder.
Okay, white holes. They're kind of like the Mysterian cousins of black holes, shrouded in a whole other level of weirdness, right?
Think of it this way. What if we hit the rewind button on everything we know about black holes? That's essentially the concept behind a white hole, a region in space-time where matter and energy are constantly being ejected outward. And nothing, absolutely nothing, can enter.
It's like a black hole flipped inside out. Instead of pulling everything in, it's pushing everything away.
That's a great way to put it. You see, a black hole's event horizon is a point of no return. But a white hole, if they exist, would have an event horizon that acts like a barrier, a point of no entry.
That's a pretty wild concept, but here's a thought, and maybe it's just me, but if they're like the opposite of black holes, and we've got evidence of black holes all over the place, shouldn't we have stumbled upon a white hole by now?
That's the catch with white holes. They're purely theoretical. We're working with concepts and equations, not concrete observations. We haven't actually observed anything that definitively points to their existence.
So they're more of a what if, a mathematical possibility, rather than something we're certain exists out there in the vast universe.
Exactly. There are also some pretty big hurdles, even conceptually, when it comes to white holes. Like, their very existence seems to clash with a fundamental law of physics, the second law of thermodynamics.
Oh, right, thermodynamics. Remind me about that again.
Well, the second law basically states that entropy always increases in a closed system. Entropy is like a measure of disorder. Things tend to get messier over time.
Right, like a cup of coffee getting cold or a neat stack of papers scattering all over my desk.
Precisely. Entropy always increases. A white hole, though, would be like that messy room spontaneously cleaning itself up, everything neatly ejected and organized. It kind of goes against the natural order of things.
So white holes, they seem to go against the natural flow of, well, everything. That's a pretty big strike against them.
It definitely raises eyebrows. For a white hole to exist, we might have to rethink some pretty fundamental physics. But, and this is where it gets really interesting, some physicists believe that white holes could be connected to black holes through these theoretical tunnels in spacetime called wormholes.
Whoa, okay, now we're talking. Wormhole, shortcuts through the universe. I'm all ears.
It's highly speculative, I'll admit. But imagine a black hole and a white hole connected at their singularities, forming this cosmic tunnel. Matter falling into the black hole could, theoretically, journey through this wormhole and pop out the other side from the white hole, maybe even ending up in a different part of the universe or another universe entirely.
So it's like a cosmic subway system. Black holes are the entrances, white holes are the exits. I love it.
Haha. You've got quite the imagination. That's a very simplified analogy, but you've got the right idea. Of course, this is all very theoretical, almost bordering on science fiction. We haven't even found concrete evidence of wormholes yet, let alone their connection to white holes.
I guess it's all part of the grand cosmic mystery. Even if they do turn out to be just a product of our imagination, the fact that we can even conceive of white holes is pretty amazing, don't you think? Makes you wonder what other mind-boggling possibilities are out there waiting to be discovered.
I completely agree. And that's the beauty of science, isn't it? Whether or not white holes actually exist, grappling with these concepts pushes the boundaries of our understanding. It sparks new questions, leads to new insights. It's all part of the adventure.
That's a great way to put it. The universe is full of mysteries, and we're just beginning to scratch the surface. Well, on that note, I think we've done some serious exploring in the realm of black holes and white holes today.
We've covered a lot of ground. The formation of black holes, the theoretical world of white holes, and even touched on the search for a theory of everything. It's a lot to digest.
It certainly is. And for our listeners, remember, the universe is full of wonder, and there's always more to discover. So keep those questions coming, and who knows what incredible things you might uncover. Until next time on The Deep Dive.